Okay, thank you all to the chairman for the very nice introduction. So without further ado, I want to start this talk. So what I going to do is to present you the the ALSIM platform, which is a suite of softwares which are developed at ESS, Engineering Software Steyr. So I'm gonna do a small introduction to the company. There was a slide missing, okay, but it doesn't matter. And then I will present you this platform, the services that we provide, and with special emphasis on a single case, which is the simulation of body in white in an oven. So we are talking about car industry here. So just to briefly summarize the story of the history of this company, it's quite young. So it was born in 2015 after the founder, Dr. Martin Skifko, decided to leave the software department of Magna Steyr, now Magna Powertrain. So the company was born in 2015 and just providing software consultancy and starting developing an SPH code. Then it has expanded since then. Now it employs, as you can see, it employs about 50 people. We have subsidiary companies in India and sales partner in China, US, Japan, and Germany. We also won a couple of awards since then. And our main business area is the car industry, as you will see, but not just that one. So these are just the distributor and the sites. As the Professor Kovny was saying, we are based and born in Steyr, which is a very nice city in Upper Austria, not too far from Germany, where I actually live. So just would like to summarize the approach of ESS respect to standard CFD companies. So the goal of this company is to release CFD softwares which are intended to be used by a very wide range of people. So not just CFD experts. So we hope to provide softwares which require minimal CFD expertise. And to do that, the solution that we propose is to personalize the software, to tailor the software to a specific application. So if you come to us with an application to develop, we will develop we'll choose the best software for you. We'll develop the specific GUI for input/output, and you get the entire software package explicitly tailored for your purpose. In this way, this will minimize the complexity of getting familiar with the software and increase the productivity of the customer. So these are some of our customers since then. As you can see, many of them, once again, are car industries. Actually, I have to apologize if in the slides you will see, let's say, many different form of templates, because the company is just undergoing a rebranding these very days. And we still have to receive the templates for the new, let's say, for anything new in the company. But you can see our new logo on the top. So what we're gonna develop is this platform, which will be also on the cloud, and we'll also provide services to the customer. So anything now is named ALSIM, and we have different specializations, as you can see. So from data cleaning to paint shop, which I'm gonna talk later, mobility, and so on. And the number of these applications is about to increase in the next future. So yeah, these are the applications that some of the applications that we are working on. So we have fluid applications, solid applications from heat transfer operations, diffusion, free surface flows, multi-phase flows, and so on. But we also have solid application concerning solid materials, from elastic and plastic deformations, hyperplastic materials, granular flows, sedimentations, and stuff like this. And to do that, this ALSIM platform integrates several solvers and softwares, which are, some of them will be two of them I will describe them. I will describe with more emphasis in the next slides, which are Merge and the LBM software. So the first product, as I said, was this SPH code, but then with time, other solvers were added, like discrete element methods, boundary element methods, affinity difference solver as well, and the lattice Boltzmann, which started in 2017 as legacy code, I would say, was just something for, let's say, just to try something new, and then has been completely rewritten starting from 2019. So now it's much better code than it was at the beginning. So first software I want to talk about is this Alsim Merge, which also was the first flagship of the company, together with this SPH code, was the first solver that the founder developed. So the Merge is a software to achieve data cleaning, because when you get a CAD file, before giving it to a mesher, you need to clean the file and improve the inevitable inaccuracies that you can find. So you have often to manually do some surface mesh generation, remove other surfaces, do some surface mesh cleaning, which takes time to do manually. So the solution we propose is Merge, which can import many kind of the inputs. You can see some of them here, 3D scans, CAD files, and so on, and can repair or merge different parts and produce also a basis mesh in 2D for 2D, 3D application, and export them in different formats and for different purpose. So as I said, it requires minimum user interaction, and it's easy to use and fast. So the improvement, when applied to a car, this relevant application, which remains the core of our interest, of our business, is significant, as you can see in this slide. Typically, you have 24 simulation a year for a car body, and you can see a very big improvement in terms of hours of computations and manual work required to generate clean, I would say, CAD files for being passed to your solver. So what can be done with Merge are, for instance, can repair defective geometries like this. It can detect cracks in the CAD file and repair in a consistent way. You can see the new triangulation here in this slide, or it can also smooth and flatten surfaces, as you can see here. Sorry, I don't see the whole of my slides. It's covered by these panels. Okay. So you can see it here. And one other thing it can do is to tackle an over triangulation situation, like you can see here. So you have too many triangles to get reasonable accuracy. And so the software can reduce the triangles to a good, according to some optimization criteria, of course, to good, let's say, enough to a reasonable number of triangles to preserve a reasonable accuracy, as you can see here from this nice picture. And one other thing which is very important, again, for the car industry, is that it can create between two different solid objects. You can think about, for instance, of metal sheets. It can create glue layers to fill the space between metal sheets. So you're producing the actual layers that you can find in real geometries. So Merge is, let's say, I would say the first kind of software that typical customer in the car industry would like to use before running a CFD software. But then it comes the core of our offer, which is this Alsim Paint Shop. So why it is important to have an effective simulation tool? So what I'm going to talk about now is an oven simulation, oven for car, and you have to think about this problem, about this phenomena, considering that an oven, that processing a car, that cooking, let's say baking a car in an oven, is the most energy consuming process in the whole sequence of steps that are executed in a plant. So of course, optimizing this process, even a small optimization in this process means a lot of time saving, energy saving, and so ultimately a lot of cost saving. And beside that, also a lot of improvement in terms of reducing your pollution. So this is why it's very important, and car manufacturers are, of course, very interested in being offered optimized solution and numerical simulations to help designing better ovens and optimizing the existing ones. So I just summarize a typical paint shop process here, which, as you can see, involves car baking, but also, for instance, e-coating processes, in which basically here you have your car, which is washed and then is dipped inside a solution to fix an e-coating layer, which this happens before having your primer, your final color. So basically every time you want to apply a different layer of color, you have to bake your car in the oven, and you have to apply many times this e-coating process as well. So once again, it's a very energy consuming process. So these are the phases of it, which we are tackling with our softwares. And just to give you an idea about the complexity of a body in white. So this is it's quite far from your the final car you drive. I mean, underneath it, there's a lot of there are a lot of irregularities, very complex shapes. So this is the typical car that goes into the e-coating phase and the oven baking, but actually it's made by, as you can see, thousands of different parts. So you can see holes, you can see irregularities. So it's very tough and challenging case. And these are the typical phases in an oven. You can see that the car goes through different steps, from a preheat up to holding another heat up phase. So you have to think of this process as very long in time. The car can stay in the oven for from 30 to 50 minutes, depending on the kind of oven you got. Each car, of course. Inside this oven it undergoes processes, I mean, involving there are several nozzles which delivers very hot air from 100 to 200 degrees Celsius at very high speeds. So we have turbulence, and we have, of course, several heat transfer mechanisms, from conduction, convection. We have radiation as well, of course. So I just put here a sort of simplified simplified picture of what happens in an oven. So you can think of this rectangle as a car. You are observing it from the top, and I just wanted to list all the, let's say, physics involved into this process. So you can see the walls of the oven or the furnace, which are at a given temperature, and you can see these red small rectangles, which represents the nozzles. And basically, each metal sheet composing which is part of the car undergoes different mechanism of heat transfer. So basically, it gains energy from convection from outside, convection inside. There is radiation from furnace wall, but it also emits energy via radiation. So all these terms need to be modeled in your CFD code. And so I just put here a very simple model, a very simplified model again of the energy balance of the single piece of the car, or of the whole car, if you like, and which lists all these different heat flux contribution, which I put in the previous slide. So radiation from external sources and so on, convection and so on. So you can see the radiation term, the heat exchange via convection here from external gas, from internal gas, and also, of course, the interaction with other solid objects. So here it's very important to have good modeling of the convection and radiation processes. So here you can just see the generic expression of the convectivity transfer coefficient and how it is correlated. This is one of the models that you can find in the literature, this Van and Apache correlation between the Nusselt number and the local Rayleigh number. Of course, this depends on the geometries, on the characteristic size of the piece of the car you are considering. So it's very challenging process. So we propose solution based on the LBM, on our LBM code inside this ASIM platform. So I'm going to briefly to give you an idea of how it is organized. Basically, we have this what we call this particle generator, which is in common with the SPH solver. We have specific input-output library. So this particle generator is basically what voxelizes the object, and we have the code then is initialized, and we have this distributor class which takes care of parallelization of distributing the load, the load between the different GPUs. And of course, we have the kernels. So the software is C++, GPU based. It runs on CUDA kernels from 9.2. And as I say, this since a few weeks is also available on the cloud. So what I'm gonna refer to now is I would say the old version of this software, because just we are currently working at the new code, which I cannot show now, which will feature as main heading the adaptive mesh refinement feature. So the existing code that we are still using in many cases is single grid. And so these are the file, the output file is HDF5. We worked a lot to improve to reduce the time necessary to print out the input files. And you can see the different kind of objects that the code deals with in this slide. So the parallelization also is 1D. So the new code will feature fully 3D parallelization. So there is not too much to comment here, just this decomposition on the on 1D. And we use this, typically the X-axis is the main axis of the composition, and the YZ slices are used for the halo and for padding. We use CUDA-aware OpenMP, and so these CUDA kernels are non-blocking, so we have MPI communication started in parallel with the main CUDA kernel. So this way allows us to have quite a good scaling, as you will see later.
You've got about 5 minutes left now.
Oh, okay. So I have to be quite fast then. So yeah, these are the main feature of the LBM solver. So I'm gonna want to go directly to the results. So you can see this scaling I was talking about. This is the oven on the event cavity typical unit test on the left, and the oven simulation on the right. And just want to show some validation that we have here. So in the next slides, you will see the probes that typically are requested by customer in this industry, by the car manufacturers. You put probes in these points, and you compare your software to the probes, and you will see, as you can see here, we are on the B pillar of the car, on the right door. So the dots are our solver, and the continuous line are the experiments. So there's quite a good comparison also for the gearbox tunnel, and also the top of the roof here. And this, you can see other comparisons here. I mean, these are not comparisons. This is just a customer case. So you can see the different points of the car, the different probes of the car here. So from the doors to the tailgates, the underhood of the car. So different temperature curves that you need to examine. I just want to show how let's say this simulation looks like via this video. So you can see the car heating up, going through the different phases of the oven. You can see the nozzles on the top on the bottom right videos passing through the car. You don't see the skid here, which moves the car to the oven just for the sake of clarity. You can see the temperature of the air as well here from these videos. So this is just a picture, how they look like. And the last thing I want to briefly to talk about is that with our code, we can also simulate inside the distribution of temperature inside the car, which is needed to determine the deformation, the stresses, and finally the deformation that the car undergoes. And to do that, we use finite difference solver coupled with the LBM. So this is just one example of coupling that we have in the ASIM platform. So the finite difference solver takes the temperature from the LBM solver and uses them as input to solve the conduction equation. And here you can see temperature distribution inside the door of a car. Okay, so this is, I think I don't have more time, but this is just the e-coating process in which with another coupling, we use the FDM for the Poisson solver and the LBM for the diffusion of ions, of electric particles during the process of painting of the car into this electrolytic solution that you can see in the video on the right. Okay, I think that's enough for the. Do I have some more minutes or?
One or two you could use if you.
Okay,
have...
I just keep then. I think it's okay. It's okay. Just wanted to, yeah, I wanted to show some SPH simulations, but the message I want to pass is that